So, for those of you that don't know me, my name is Lawrence Sandler, and I'm responsible for applications engineering at Epic Solutions. You have to excuse the title here. I claim no responsibility for that. That was John Orlando's contribution, so you can talk to him about that. But the subject of the talk is on Thunderbolt 3. How many people are familiar or use Thunderbolt 3 now? Okay, a few of you, not a lot. So what Thunderbolt 3 is it's basically a tunneling architecture that allows you to use multiple different protocols. Sorry, can everyone hear me now? All right. So it allows you to use a variety of different protocols. So it supports USB, USB 2, USB 3, supports DisplayPort as well as PCIe. So you get 4 lanes of PCIe Gen 3, and that's really what we're so excited about. What it looks like physically is you get a cable. On both ends of the cable, you get a USB-C connector. So if you want a legitimate Thunderbolt 3 connection, that USB-C connector will look something like this with a lightning bolt and an actual number 3 on it. And that basically tells you that this cable can support 40 gigabits per second throughput. Why do we want this? Why are we so excited about this? Well, with SDR technology where it is and where it's going, we're always getting to higher bandwidths and higher channel counts. So we always want higher bandwidth. If you have high bandwidth, you can always go lower, but the higher the better, basically. We want low latency, and we want very deterministic paths. So we want deterministic latency on all of our lanes. PCIe is really good at that. And nowadays, Gen 3 is pretty well deployed, so it's commonly available on a lot of hosts that you probably already have. Thunderbolt 3, that one small cable, holds 4 lanes of PCIe Gen 3, and so you can get up to a 40 gigabit per second throughput on that cable. The 4 lanes of PCIe Gen 3 gives you 4 times 8 gig at the raw speed. There is some coding on that, so not taking into account any particular efficiencies, you get basically a raw throughput of almost 4 gigabytes per second, all over that one little cable. So it's really nice, really easy transport capability to go from your SDR to your host system. Another thing that's really nice about it is a lot of the host systems take a laptop that you have that might have the Thunderbolt 3 connection on it. You don't have to add an additional driver. There's no drivers to fool around with. You basically have to turn on that PCIe capability to that connector. Once you're there, it just works, basically. So a couple of real-life examples. We do have a couple of SDRs that we already use Thunderbolt 3 on, one being our X4 system that gives you a capability of 100 megahertz IBW. It also gives you capability of 4x4 MIMO, and we, as you can see in the picture there, we connect it up when it's installed in this platform right to our host with that one cable. Another one is our new Sidekick Stretch that we have in a Thunderbolt 3 enclosure that we call Thunderkick. This is being shown at our booth next door, so please come by and take a look at this. So everything runs, PCIe is basically extended through that cable, and it's also powered with that Thunderbolt 3 cable. So that's basically it, and thank you, everyone.
Mike from Millennium Space Systems. I'm a RF and comms engineer there. So just wanted to talk to you very briefly about Millennium. I think this is our 4th year at the conference. At least for me it is, and I think we sponsor it every year, so awesome to come back here. Some of you might notice a rather unsettling change to our logo. I mean, we love Boeing. But yeah, we're a really awesome place to work. We work on a ton of stuff that you guys work on. We actually have a satellite in space right now running GNU radio and RF knock. So that was really cool to be a part of. We're working on more of that. We work with a lot of RF knock stuff, so I was really excited to see the UHD 4.0 talk that the EDIS guys gave. But yeah, we do a ton of stuff, Python simulation, FPGAs, DSP, we do everything there. So basically if there's something that we're trying to do, instead of buying it, we like to build it ourselves. So that gives you a ton of opportunities if you want to come work here and do cool stuff. So yeah, that's all I have. If you want to hear more, come find me or talk to Rigo. We also have a booth over there with like stickers and stuff. So yeah, thanks.
All right, hi, I'm Tim O'Shea from DeepSig, and I wanted to tell you a little bit about the Omnifi Modem, if you haven't seen it in the lab there. So the whole idea, our company is really looking at how do you infuse machine learning into communication systems to reduce power consumption and to help radio signal processing algorithms fit the world better. So all those assumptions we made, so assuming a perfectly synchronized system, assuming a perfectly Gaussian channel, we make all kinds of assumptions every day when we build modems about nice idealized channel models. And really much of what we're looking at is how can we drop those assumptions and actually improve our systems in real world data and conditions and interference. And so a core of what we're looking at with Omnifi is, well, how do we take a machine learning system and treat it as or how do we take a comm system and treat it as a machine learning system? And so this is a basic construct that we call the channel autoencoder. And this is an idea of representation learning where you take two neural networks, one that learns to convert bits into samples to transmit, and one that converts the received samples back into the estimated bits. So this is really the core of what a comm system is. And so we try to cast this as a neural network. And there's this great example here. You see this is the canonical case of encoding 2 bits into 1 symbol. And we don't ever tell it what QPSK is or what slicing is or any of these things. We simply try to minimize the bit error rate. And you can watch this thing converge here. And it will wind up with 4 nice QPSK-like points that just drive the bit error rate down. So this is kind of a great example. It learns something that we're used to, we've seen for a long time. Now, one of the problems is doing this over the air. You don't have a gradient to backpropagate through if you want to train the transmitter. And so you have to do a lot of tricks to come up with a way to do these updates over the air. And what's exciting there now is you're actually approximating the gradients over this channel, which can now extend to be much more complex than just a Gaussian channel. This could include nonlinearities from power amplifiers, from other RF components. This could be interference that's present in a wireless channel. And so what you're seeing here is an animation of Omnifi in the demo we have next door, starting with a completely random constellation, transmitting this out over a USERP, receiving it on another USERP, and then you're watching here the symbol error rate decrease. So it just starts basically optimizing this constellation and coming up with a better representation. So again, here you see it arrived at a QPSK constellation, which is a great way to pack 2 bits into 1 symbol if that's something you like to do. All right, so we've started to, I'm going to do this out of order. So let's ignore this slide for now. Okay, so what's really exciting about this now, we can train any sort of information rate with this. So we can learn 16 QAM systems. We can start to learn larger block codes. So since you can pick the rate you want to design for, you can start to have it design optimal constellations and encoding and decoding blocks for this over the air. So what you see here is, again, we've trained, this is now a 16 QAM constellation that started totally random and is decreasing. The symbol error rate is just going down. And then here we have, this is actually 8 bits being packed into 4 symbols. So it's basically a 4x 256 QAM that's learning how to create these big block codes to encode 256 values. And so you can see this is also decreasing and will eventually converge to this really interesting noise-like constellation that's been optimized over that hardware, for that link. Right, so this is exciting. We can now learn these one-time use waveforms. We can learn this on specific hardware. We can learn error correction that's specific to these links. So we can now use this for real applications. So we've started to look at this for like UAS comms, where you want resilient links that you might have poor, small amplifiers that have lots of distortion on these things, and then you might also have interferers and even malicious interference in the environment. And so this is really nice because you can continue to optimize to compensate for the hardware effects as well as for any other effects in the air. And so here we're showing, using that same learned constellation, we can transmit streaming video from a UAS or from another platform. And we can also do this for any sort of IP traffic like Mavlink and AES-256 encryption on top of it. And that's it. So we're also starting to look at applying this into the 5G space. So there's a lot of pieces of the 5G waveform that are very computationally complex. And so we've started to show that both on the transmit and the receive side of the G-Node B, there's ways that you can really drastically drive down the power consumption and allow this to exploit experience and measurement from a base station after deployment. So here you see a case of an equalizer where you allow it to continue learning how to equalize better after deploying this base station. And this can give you a significant increase in bit error rate over using a traditional kind of MMSE-based approach that has to rely on noisy channel estimates from sparse references. Right, so that's it. Come chat with us if you're interested in either of those, or if you're interested in working with us. Thanks.
So Rob Miller, one of the researchers at Prospecta Labs. This talk, or lightning talk, I should say, falls into one of the shameless plug categories. So what I'm going to do is just very briefly say, hey, super excited to be here, bronze sponsor. Probably more excited about the fact that this is the second year in a row where we have the same name. So yeah, very quickly, date back to AT&T Bell Labs Research Department. We're essentially kind of the same people doing the same research 6 or 7 names later. So definitely doing a lot in this realm, using GNU Radio all over the place, and excited to basically do one of 2 things. Number one, just talk a little bit about the research that we like to do and shamelessly beg for people who have signal processing skills in GNU Radio to come talk to us about full-time jobs or internships or what have you. And then the second part of this is also to introduce a workshop that we're putting on at 2 o'clock today in Atlantis, which is about interference mitigation. It's going to be pretty interesting. I'll talk about it very briefly in slide number 3. Again, only 3 slides, so jumping through. Heritage there, Prospecta Labs, might know us better as Telcordia or Bell Labs Bellcore research arm, primarily located in New Jersey with a new office in Maryland. More than half of the staff are PhDs, very much value academic rigor, but then also implementations and prototypes, a lot of which we use GNU Radio for, and then also IP development, actively participating in a bunch of telecom standards and industry bodies as well. There are 250 people in the labs. There are 5 of us here at this conference. We are all from the Wireless Networks and Systems group, which is the biggest group that we have. There are a bunch of other very large departments, specifically the cyber one is growing, so if you have those interests, again, please see anybody with a Prospecta Labs badge. Also very big in data science, data analytics, and some broadband optics departments as well. We do have a commercial solutions offering in monitoring smart grid anomalies as well. So that's who we are. Again, we're hiring. Now, intro to co-channel awareness and mitigation workshop. Again, 2 o'clock, Atlantis, right next door. There's going to be a couple of interesting parts. So first, we're going to talk about the problem of co-channel interference and a lot of the techniques and options you have of dealing with it, both detecting and then mitigating it. There are a lot of techniques, so we're going to give a little bit of an overview of that. There's single antenna techniques, but our focus for today will be on array-based techniques. So we will provide an array of array-based techniques. Now, the guy leading, I guess, the technical aspect, thank you, Ben, the technical aspect of this workshop is Joe Liberti, who wrote a book a while back that's pretty popular in this area. He is a Hokie for half the room who are also Hokies, just so you know. We're going to go into some of the math and some of the theory, but we're not just going to sit there and stare at equations. We're also going to release a bunch of incremental GNU radio flow graphs that will demonstrate those principles for the first 2 hours of this workshop, which is going to be kind of neat. All of those utilities are available at our Perspective Labs GitHub accounts. If you go there, you can download. They're openly available to play with. I will say that to actively participate in the workshop, we recommend GNU Radio 3.8. If you don't have it installed, you've got maybe a couple of hours to try to get it installed. If not, we do have about 10 USB drives with virtual machines installed, so you can just grab them and participate with VirtualBox. At the last 45 minutes of our workshop, we're actually going to do a capture the flag, essentially the flag. We're going to have a mini capture the flag. There's going to be one flag where you're going to have to essentially use the flow graphs we're going to release and the signal processing utilities to try to capture and decode the flag. The winner is going to get a Lime SDR Mini, which is a nice multi-antenna SDR if you're not familiar with it. And with that, I will jump off stage and say, again, interested in internships or full-time jobs, come talk to us.
Thank you, Rob.
Thanks.
Hi, everyone. I am Bowen Hu, which is I am one of the students who participated in the Google Summer of Code this year. And I am a student from Fudan University, Shanghai, China. Well, yet another university you may never probably heard of. So, yeah, I tell you, they're very good at teaching Chinese. Oh, yeah. So, the GR Verilog, the out-of-tree module, is the outcome of this 3-month project. So some of you may have attended the RFNOC workshop this evening. This morning or yesterday. Actually, the one thing you may have learned from it is that it's going to take you several hours to compiling your Verilog design into bitstream. So so the thing you really want to do is you want to really verify your design before you're compiling it. So it will certainly save a lot of time and will speed up your iterations. And the GR Verilog is the module that could help you with that. It actually is like a simulator. So we could have a demo here to show how it works. This is a video. Can we play it? Oh, it's playing. So basically, maybe you cannot say it because it's too small, but essentially you just, there is a Verilog AXI block. You just choose the name of your Verilog design, and it will automatically compile your Verilog into C++ model, and it will generate a shared library and load this shared library at the runtime. And eventually, your Verilog design would become a block, and it will run at the real time in GNU. And here we go. We could show, you see, this is a doubler, which is similar to the example that offered by RFNOC workshop. They do a GAN example, which just multiply something by the constant. And this is one, except this is one just multiplied by 2. By the way, you can notice the data type of it is really a float type. Actually, internally, there is a floating point to fixed point convert function, but you may want to tweak to fit in your design of this function because your design might not be the one that we offered. So here is, maybe we offer another example that's more complicated than the multiply by 2 one. So what I want to do is we show the next demo is add by 10. So it's really complicated. And as for why, you could just show that, and I'll explain the reason. So it is playing now. Oh, yeah. You could say the green line is the input, and the purple line is the output, and the shifted by 10. So it is just a demo of add by 10, but what really it does is really complicated, because actually I am not using some pure logic to do that. Actually, this program is running on a RISC-V CPU, and we do a software memory mapping to the address, and actually this CPU is kind of like a virtual hardware and running an actual software on it. It is like C code. If you want to know about, if you want to say about the C code, you can find me here. Actually, it just take the input, and there is some memory mapping things, and add it by 10 and get it to the output port. Yeah, basically that is. If you want more information, you could say you could go to say my poster at, I believe, in the next room. And if you have anything you want to talk about me, you want to talk with me, you really could find me here throughout the conference. Oh, that's all. Thank you.